Hello everyone and welcome back to Math 327. I hope you've had a really good break. I'm going to be taking over as your lecturer for the next 4 weeks, weeks 9 up to week 12, and then both Kwok and I will be giving the lecture in week 13. Over these 4 weeks, we're going to be looking at a special type of abstract measure space, which is known as a probability space. And we're going to be changing to a different textbook for these 4 weeks, which is this textbook by Durrett, which is available online. And the link will be up on Moodle so that you can download it. And we're going to be going through some selected sections of the first 4 chapters of this book by Durrett. Now, in this week's lecture notes, I've included a whole bunch of other resources for you, and they're all optional. So the lecture notes, as well as the reading from Durrett, is, as well as your tutorial exercises, is enough for you in this subject. But this is more for people who are looking to read further into the topic, or say after you finish this subject, if you then go on in honours or in your PhD to do more work in probability, then these resources might be useful for you then. Also, if you're struggling a little bit in this subject, then some of these resources might be able to help you out. There's this other book by Axler, which is also available online. It only has 1 chapter on probability, and really that's only enough for this week 9 lecture. It doesn't cover what we're going to be talking about in the later lectures. But it does give a very accessible introduction to this topic of probability theory, and it's more about connecting it back to the measure theory that you've already done in the first 8 weeks. So having a look at that chapter might be useful for you as well. I also recommend a couple of other books that are mainly probability books. Rosenthal is quite a heavy read, particularly at the undergraduate level. But if you're really comfortable with what you've done so far in weeks 1 through 8, and you want to read in a lot more detail about applications of measure theory in probability, then this book I definitely recommend. The library has 1 copy though, and as far as I know, there's no online version of that book. Another book that you can also look at is this one by Jacob and Protter, and it's a bit more accessible than Rosenthal. So it might be another good option if something in Durrett or in the lectures doesn't make sense to you. Of course, come along during the lecture times and I'll be available on Zoom to discuss with you. But also you can have a look at this book, and the way that they explain it might make a bit more sense to you. There are some more resources at the end of this PDF, which I'll just briefly show you now. So I've got some YouTube videos up here. If you want somebody else to explain the same topics in a different way, then particularly this first video series by Jeff Miller, who calls himself the mathematical monk, is a really good introduction to measure theory and probability. And if you're wanting to revise material from Stat 101, then this lecture series by Joseph Blitzstein is also very good. There's a very wide variety of statistical background amongst all of you. Some of you haven't done Stat 101 at all, and it's been several years since you last did statistics. Others of you have already done all of second year stats, and some of you are even doing a PhD in statistics. So, but because we're starting from the very beginning and the very basics, I think this topic, these 4 weeks, should be accessible to all of you, because you've all had the previous 8 weeks to know what a measure is, and particularly in week 8, what an abstract measure is. And so this material in probability measure should all be quite familiar. The references that I've listed in these lecture notes are at the end here. And there are links here for you to find out more about some of these. None of this further reading is compulsory other than the chapters from Durrett. And we're only really looking at the very beginning of chapter 1, like the first 8 or 10 pages of Durrett today. So to start with in this lecture, I'd like to give a bit of motivation and a bit of an overview of the idea of a probability measure space. So we are going to be going beyond the basic idea of probability that was introduced in Stat 101. And in particular, we're going to be redefining everything in terms of measure theory in a mathematically rigorous way. And so this is then going to link all of the mathematics that you've studied in your degree with this study of observed data and statistics. This is useful because it unifies the ideas of discrete distributions and continuous distributions that we covered in Stat 101. So you've seen how with discrete distributions, when we're taking the expectation, then we take a sum over the discrete distribution. Whereas with a continuous distribution, we have this thing called a probability density function, and we integrate that function to calculate probabilities in continuous distributions. But not every random variable can fit into that classification of discrete or continuous. There are random variables that are neither or both, depending on how they are used. And so with measure theory, we can make much more general statements and proofs that apply to all types of random variables, not just random variables that are defined on the real number line, which is what we were limited to with what we've done in Stat 101. Now, it still sometimes can be useful to restrict ourselves to just looking at real valued random variables, but I'll try and be careful to make the distinction when we're making that assumption of a real valued domain versus when we're looking much more generally at an abstract probability measure space. Some of you quite soon might be applying for jobs or writing research proposals, and I would encourage you to consider the next 4 weeks as an exercise in explaining how mathematics, even very pure and abstract mathematics, can be related to real world problems and issues. And this is a skill that's very important to develop, whether your future career is in research or in industry. To give you some concrete examples where these sort of applications arise, we can think of things like random functions, so ordinary differential equations or partial differential equations. There's a field of applied mathematics called inverse problems. And what we're doing there is not really inverting these functions, but rather we're looking at the pre-image of the function to see which parameters of the function are consistent with some observed data. So that's essentially the idea of an inverse problem, is we take some observed data that we believe is representative of some PDE, like say the heat equation, and then we want to look at the parameters of that PDE that match the data that we've observed. We can go even further than that into the realm of stochastic differential equations. And that's where we're looking at things like the Ito calculus for random functions. We can also look at other types of random variables, like random graphs, which are used in social network analysis. And these are interesting because a random graph can be thought of as a discrete random variable that might be very high dimensional. But often when we analyze these networks, what we're really looking at is in the limit, as the size of the network goes to infinity, we end up with a continuous distribution. So random graphs are an example of a random variable that doesn't actually fit neatly into those two separate categories. It's a little bit of both. And so that then means that the sort of calculus that we need to use when we're taking expectations and calculating probabilities is based on measure theory. You also might have gone to a few research presentations about operator algebras, particularly in this department at Wollongong. And if you have an algebra on a measurable space, then you can turn that into a probability measure. And in particular, things like Banach spaces and C-star probability spaces arise in the study of random matrices with various restrictions on the form of that matrix. So for example, you might look at the distribution of random matrices that are positive definite. Or you might look at the distribution of the eigenvalues of those matrices and the eigen vectors of the matrix. There is a topic that I will want to cover eventually in this subject, which is looking at the idea of a random measure. And this is a special case of a random function where that function has to satisfy all of the properties that make it a valid measure. And so we can then look at random distributions over measures themselves. I mentioned that there's also going to be new topics in the next 4 weeks. And one of the major topics is we're going to be looking at a special way of taking the derivative of a measure. Now, a measure is a function, but it's a special type of function. And so we're going to be looking at a special type of derivative, which is known as the radon-Nikodym derivative. And this is used in situations where you have what's called a change of measure. In particular, it's used in Bayesian statistics when we have Markov chain Monte Carlo algorithms for computing integrals of Bayesian probability spaces, and in particular, when we have distributions where the number of parameters can change, then we need trans-dimensional algorithms where we can actually go from one space in RD, for example, to another space that's in RD plus 1. And we also need that jump to be reversible. So there's this idea in MCMC of a reversible jump in between dimensions, and that relies heavily on measure theory and the radon-Nikodym derivative. So hopefully all of that has got you keen to get started. This is part 1. There'll be other videos up on Moodle going this week through an explanation of the definition of a probability measure and a probability space. Next week, we're going to be looking at random variables and defining them in terms of measure theory, and also looking at another type of measure, which is the cumulative distribution function. In week 11, we're probably going to be looking at that radon-Nikodym derivative and also looking at probability density functions and how to define them in a mathematically rigorous way. And then in week 12, hopefully we'll have a bit of time to look at this idea of completely random measures. Week 13 is going to mostly be a revision lecture. As I mentioned, both Kwok and I will be giving part of the lecture in week 13, and there might be some leftover topics that we haven't had time to get through in the rest of the subject that we might briefly mention in week 13, but most of that week 13 content isn't going to be on the exam because your exam is very soon after week 13. So we want to give you enough time to revise and prepare for your final exam.